Which do you think has higher energy? A gram of uranium or a gram of rose petals? Gram of uranium or a gram of rose petals? They're the same, yeah. So if you could fully react them, because E equals mc squared, it does not matter what the item is. It just matters what the mass is. So that mass of uranium can convert to the same energy, which would be on the order of 10 to the 14th joules. If you just put 1 gram in for mass, and convert it to joules for E equals mc squared. If that was a gram of rose petals, it wouldn't matter. A gram of whatever will contain the same amount of energy. It's just we found a way to harness the uranium and not rose petals. Okay? But everything, you also would contain that amount of energy. That's doing the nuclear reaction fission. So going from larger nuclei to smaller nuclei. Okay? We can also do the reverse, but it involves the same sort of calculation. And one place where we see that is what's called the nuclear binding energy. Nuclear binding energy. This is the same sort of calculation that we did before with E equals mc squared. It just will not give you the reaction. So in this case, the reaction is not given. You have to figure it out by yourself. But we'll ask you, what's the nuclear binding energy for helium? And you'd have to figure that out. So let me show you how that works. Say we have helium, and helium has how many protons? 2 protons and 2 neutrons. To make a nucleus, say, that would look like this. To bind that together, aka to make this, we would have to mix into our little bowl 2 neutrons and 2 protons. We stir that up, put in a little bit of energy, and we can make our helium nucleus. That has 2 neutrons and 2 protons. Okay? So the reaction would look as follows, or what you would see in your cookbook, in your chemistry cookbook, would say 2 protons plus 2 neutrons goes to helium. And let's put in the numbers as well. So proton is 1, 1. 1 on as the subscript, meaning the number of protons. 1 in the superscript, meaning the number of protons and neutrons. This is 1, 0 for a neutron. And then 2, 4. Let's see if this adds up. 2 for the subscripts. 2 times 1 plus 0 equals 2. For the superscripts, 2 times 2. 2 times 1 plus 2 times 1 equals 4. So there we go. There's my nuclear binding energy. If it was any atom, it doesn't matter what it is. You just have to add it up. And this is the reaction for making the nucleus, or what's called the nuclear binding energy. Okay? And so if you wanted to find the energy of this, you say, okay, change in energy, change in mass times c squared, change in mass equals the mass of products minus the mass of reactants. That would be the mass of helium minus the mass of the protons times 2 minus the mass of the neutrons times 2. You multiply by 2 because there's 2 of the protons and 2 of the neutrons. You go through the same calculation as before and you can find that mass. You would either have to look up, if you're doing a homework problem, or be given on the test the mass of the neutron, the mass of the proton, and the mass of a helium nucleus. Okay? Which you could, for example, look helium up, say, on your periodic table. But what's the problem if you look helium up on the periodic table? There's 2 problems, really. Yeah, the major problem, well, one of the major problems is it's all the isotopes averaged together. But here, we're only making helium-4. So you don't want to use your periodic table to get numbers for this. We'll give you those numbers, or you look it up more for a particular nucleus. The other problem is we're not going to get enough significant figures in the periodic table. So we're going to give you a number of significant figures to do this type of calculation. It'll usually be about 5 sig figs, so there'll be quite a few.